So we identify the different orbitals with a number and a letter. The orbits were just labeled 1, 2, 3, 4, 5. Kind of boring. The orbitals are also given numbers, 1, 2, 3, 4, 5. That's called the principal quantum number. And that's the principal shell of the orbital. As that n number gets larger and larger, the energy increases. And the size of that volume where the electron is likely to be gets bigger and bigger. Then we have a letter, and that indicates the subshell. Okay, that specifies the shape of the orbital. And the possible letters are S, P, D, and F. You might wonder, why not A, B, C, D? That would make more sense. These actually there's historical meaning behind those. So we'll leave it at that. So this is all going to be a little confusing, and then I'll give you a crazy analogy at the end, which will hopefully make you want to run screaming into the night. No, hopefully help you to remember some of it a little better. So the 1s orbital, that's the lowest energy orbital. So if we took like multiple exposure pictures of an electron, we might get something like this, where, every 5 seconds we're taking a picture, where's the electron? Oh, one time it's, over here, and another time it's over there, and another time it's over there. And we'd see that this gives us a spherical distribution. And it's kind of fuzzy along the edges because there's not a distinct line that the electron cannot cross. But this dot density shows us where the largest probability is to find the electron. We can also use more of a geometric shape to represent. Those dot pictures are a little difficult and tedious to draw all the time. So we can say, well, let's just make it a nice sphere, and that usually is drawn to represent where 90% of the electrons, 90% of the time the electron would be found within the sphere, but 10% it would be found without. So maybe 90% of the time you'll find Andrew in the house, but 10% of the time he might be running away somewhere. Okay? So if you see, if we superimpose these, we see that there are times when the electron is outside of that sphere. We understand that. So the single electron of an undisturbed hydrogen atom, there are days when I'd like to be an undisturbed hydrogen atom. Undisturbed hydrogen atom, it's not being zapped by electricity or stressed out by its children or anything. It's just sitting there. The electron is going to be in its lowest energy state, which is going to be that 1s orbital. That's called the ground state. The electrons are generally going to seek out the lowest energy, just like if you put water onto a bumpy surface, it's going to go into the lowest depressions. But the electron can jump up to an orbital that has higher energy. Just like in the Bohr model, it jumped up to a higher energy orbit. And that's called an excited state. An excited state is unstable. A little bit like teenage boys. Okay, so the newest video games comes out, and they get excited, and they get up, and they go to the store, and they get it, and they play, and then they revert to their ground state, which is comatose on their bed, right? They sleep a lot, those teenage boys. Okay, so all atoms have one ground state, one lowest energy state, and they have multiple excited states. They can be a little bit excited, they can be a lot excited. So we talked about n equals 1. That principal energy level 1, it only has one subshell, the s orbital. N equals 2 has two subshells, an s and a p. The 2s orbital is the same shape as the 1s. It's spherical, s spherical, but it's bigger. So just like the second orbit in the Bohr model was larger, the second orbital, second level, is larger as well. So this is larger and higher in energy. And then there's the P, subshells. The p subshell has 3 different orbitals, and these remind me of balloons, or they're sometimes called dumbbells, dumbbell shape. So here's the dot probability model, and here's the geometric shape. So they've got this node in the middle, because you can't have an electron in the nucleus, right? But the electron may be over here or over there. So there's this one that's arranged around the x-axis, this one along the y-axis, and this one along the z-axis. So they're perpendicular to each other. They don't overlap with each other. But they all have the same energy. You confused yet? Yeah. Try to stay with me, and hopefully we can clear it up. So this is a graph, or a chart of sorts. Here are the shells, that principal energy level, n equals 1, 2, 3, and 4. As it turns out, the number of subshells is equal to that number. So n equals 1 has 1 subshell, n equals 2 has 2, n equals 3 has 3, n equals 4 has 4. And the letters go S, P, D, F. So in the first level, we only have S orbitals. In the second, we have S orbitals and P. We've got 2 kinds. In the third level, we have S, P, and D. There's 3 kinds. So pictures help. So in that third level, there's 3 subshells, S, P, and D. The S and P are the same shapes as the S and P in the lower levels, but they're larger and higher in energy. And then there's the D. The D subshell has 5 orbitals. Aren't they pretty? You don't have to know how to draw those at all. I'm just showing them to you. So the first 4 are like, well, okay, that's just kind of an extension of the P, right? Instead of 2 balloons, it's 4 balloons, and there's 4 of them, and they're arranged, in these different planes. And then there's that one. That's like a p orbital that can't swim, and so it has a life preserver around its middle or something. I don't know. So the way that they got these shapes was using mathematical equations. So they didn't just think these up. There's a lot of math behind this, and we definitely don't want to talk about that kind of math. What we are interested in is a way to specify what sublevels and orbitals and shells the electrons are located in, because that's going to help us understand why hydrogen is very reactive and why helium is not very reactive. So for a hydrogen atom, simple atom, it only has 1 electron. We're starting small, where it's a little easier. So that 1 electron in the ground state is going to be in the first energy level, n equals 1. And there's only 1 sublevel there. It's the S sublevel. And so this is the 1s, and then it has 1 electron in there. So this superscript is the number of electrons, and this specifies the orbital. So this is telling us there's 1 electron in the 1s orbital. Hang on a minute here, I want to make sure. Okay. I want to jump ahead to this. Okay, this is the quantum hotel. This is a crazy analogy, I promise you. The quantum hotel, a discount resort for electrons in Mrs. K's chemistry land, which you may not think is equivalent to Disneyland, but I like it. One of the hard things, I should say, about the quantum mechanical model is it's so abstract. The Bohr model, you can envision, like the solar system and electrons orbiting, right? The quantum mechanical model is really, really tough. And without any visual picture, it's really hard. I'm a visual person. I have to have pictures. And so I tend to relate things to everyday life. So the quantum mechanical model is a bit like kind of a weird hotel. So in this hotel, this would probably be located in Las Vegas because there they have some pretty strange architecture, right? They have one that's shaped like a pyramid. This would be shaped kind of like half of an inverted pyramid. So the first floor in this quantum hotel has one room. And that's called the S room. It's on the first floor, so that's 1S. The second floor has two rooms, the 2S room and the 2P room. The third floor has three rooms, the 3S, the 3P, and the 3D. The fourth floor has four rooms. There's a pattern here, right? 4S, 4P, 4D, 4F. You with me? Okay, so those floors in the quantum hotel correspond to the principal energy levels or principal shells of electrons in the atom. Each room corresponds to a subshell. Okay. Now, in these rooms, these are kind of odd hotel rooms. The S room, all S rooms have one bed. That's not so weird. P rooms have 3 beds. That's a little strange. D rooms have 5 beds. Have you ever seen a hotel room with 5 beds in it? Me neither. That would have been handy on some of our family vacations, but they don't exist. And the F rooms have 7 beds in them. The beds represent the orbitals. So the S sublevel only has one orbital in it. The S room in the hotel has 1 bed. The P sublevel has 3 orbitals. Let's go back and look at the picture of that. Okay, it has 3 orbitals. The P room has 3 beds. The D room has 5 beds. The D sublevel has 5 orbitals. And we don't even want to think about the pictures of the F orbitals. If you think these are weird, the Fs are even stranger. So does that make a little more sense now? Can you kind of envision the structure here? Can you picture the hotel though? Okay, 1 room on the first floor, 2 rooms on the second floor, 3 rooms on the third floor. S room, the next floor, S and P, the next one, S, P, and D, the next one, S, P, D, and F. The S room has 1 bed, the P room has 3 beds, the D room has 5 beds. How many people can sleep in a bed? 2. We're going to be reasonable here, right? 2 people per bed. They do have some rules at this hotel. 2 people per bed. So you can only put 2 electrons in each of those orbitals. And in the hotel, if you stay on the 4th floor, they're going to charge you more than if you stay on the 1st floor. So money equates to energy. So higher energy, higher floor in the hotel. So an electron that's on the 4th level is going to be higher in energy than one on the 2nd level. Okay? So let's go back here to where we were. So these electron configurations then, we can kind of think of them as these might be the notes that the hotel clerk is taking, trying to keep track of what rooms are full so that if some more electrons come in, he can, send them to an empty room. So this would tell him that there's 1 electron staying in the 1s room. Another way, that's electron configurations. We can also use orbital diagrams. I like these because they're a little more visual. Orbital diagrams represent each orbital as a box and each electron as an arrow. So for hydrogen, we'd say, okay, well, here's the 1s orbital, and it has 1 electron in it. So the boxes are like the beds in the rooms. In those orbital diagrams, the direction of the arrow represents electron spin. So it's not exactly true, but it's convenient to think of the electrons either spinning clockwise or counterclockwise. Say positive spin or negative spin. And there's something called the Pauli exclusion principle. The orbital can have no more than 2 electrons, and they have to have opposite spins. That's symbolized as two arrows pointing in opposite directions. So there's a Pauli exclusion rule at the hotel that you can't have more than 2 electrons per bed. Electrons are like the people. You can't put more than 2 people in a bed. And they have to have opposite spins. So I've changed what that means a couple of times. The latest incarnation is there's some guy convention, and so these are all guys staying at the motel. And I don't know how many of you know this, but guys don't like to share beds with other guys if they're not romantically interested in them. They're like, I'd rather sleep on the floor. They don't allow sleeping on the floor here. So what happens is the first guy gets into the bed, and the next guy's like, man, they're going to make me sleep in the bed with this other guy. I'm going to sleep upside down in the bed, so there's no hanky-panky going on. So the other guy sleeps with his head at the foot of the bed. Okay? That's equivalent to this spin up, spin down business. So if this was the one, I didn't mean to do that in orange, but that's okay. If this was the 1s orbital and it had 2 electrons in it, the first one is going to sleep right side up, and the second one is going to sleep upside down. So they're going to be opposite spin. The scientific explanation for that is it's lower energy if they're paired up like that. Yes?
Like the Einstein thing where it's how they're trying to pass information through long distances by figuring out how electrons are spun, and that they were going to use that binary code to pass information instantaneously from one direction to another.
Probably.
Complementary to each other.
Yeah, probably it is related to that. And sorry, you two people, I can't repeat his question.
And it was like, I think it was like Einstein that was that said it was like a pair of gloves, and then scientists were like, no, it's quantum, so as long as it's not measured, it's not spinning in any direction until it is measured.
Yeah, one of the really freaky things about this wave-particle duality is that it could be acting as a wave or a particle. Until you observe it, it's really, you could say it's doing both. You can also say that the electron is everywhere and nowhere until you observe it, and then it's in one place. Yeah, it's going to make your brain hurt. In a good way, I guess. So let's draw electron configurations and orbital diagrams for helium and for lithium. So the first thing we need to figure out is how many electrons does helium have? 2 electrons, right? Because it's element number 2 in the periodic table. That tells me it's got 2 electrons, it's got 2 protons. I like to draw the orbital diagrams first, so we're going to do those first. So here's my orbital diagram. So that is the 1s, that's the lowest energy one. Because these electron guys that come to stay at this hotel, they're cheap. It's a discount hotel after all, discount resort. And so they want to stay in the cheapest available room. So they're always going to pick the cheapest room. The cheapest room is the 1s room. So we've got 2 electrons needing to stay here, and the first one comes in and claims sleeping right side up in the bed. And the next electron comes in, and he's going to sleep upside down. They're going to stay in that same room because it's cheaper than taking a separate room. So that's the orbital diagram. From the orbital diagram, then it's easier to write the electron configuration. So this is more of a shorthand. So in the 1s orbitals, we have 2 electrons. So that's the electron configuration for hydrogen. Let's do lithium. How many electrons does lithium have? 3. So I'm thinking about the quantum hotel, that this box is already full. We're going to need to go somewhere else. On the second floor, I'm just going to draw out the whole second floor. So this is the 1s sublevel, this is the 2s sublevel, and this is the 2p sublevel. because there were 3 beds in the P room. S rooms only have 1 bed. Each bed can hold 2 electrons. So we could put up to 6 electrons in this room. But this room costs more than that room. So we're going to put them in as cheaply as possible. So the first electron is going to take the cheapest room and sleep right side up in the bed. The second electron is going to sleep upside down in the cheap room. The third electron can't stay in that room because it's full. So he's going to have to pay more money, higher energy, and go into this room where he's going to choose to sleep right side up in the bed, because who wouldn't, right? So how would we represent that? The electron configuration will be 1s, 2, 2s, 1. This is a case where chemists do write the number 1. I'm not going to write anything about 2p because it's empty. So I'm only going to write things that have electrons in them. So 1s2, 2s1. Any questions? Okay, so when you have more than 1 electron, the subshells within the principal shell don't have the same energy because of interactions that occur between the electrons. So we see that the 2p room is more expensive. It's higher in energy than the 2s. The 3p is higher in energy than the 3s, and then the 3d is higher in energy still. I think of that in the hotels a little bit like, well, you're paying to get further away from the noisy elevator and ice machine, right? Because if you sleep here by the elevator, this might be the elevator, people are going to get ice at 3 in the morning and wake you up. People are going to come in from a loud party and wake you up. And the farther away you get, the quieter it is. I'm making this up as I go along. The other unfortunate thing for students is that this first room in the 4th floor, you would expect this to cost more than the D room on the 3rd floor, right? But it doesn't. It's actually a little cheaper. And so we get this intermingling of these levels in terms of energy, and that makes things harder to understand. So in the analogy, I say there's some Groupon coupons, right? And so there's some deals that make this room cheaper than that, okay? And I'll show you later how to figure out what the deals are. Okay, so let's write the electron configuration and the orbital diagram for carbon. How many electrons does carbon have? 6. So here's carbon with 6 electrons. And again, I'm going to do the orbital diagram first. So on the first floor, there's the 1s room. On the second floor, we have the 2s room. We also have the 2p room. And let's see if that's enough. Otherwise, we can draw more. So I need to put 6 electrons in. So the first electron is going to take that cheapest room and sleep right side up in the bed. So positive spin. And the second one's going to take the cheap room and sleep upside down in the bed. The next electron has to go up into a more expensive room, a higher energy subshell, and it's going to have positive spin, sleep right side up. The fourth electron is going to sleep upside down. Yes?
Each subshell has to contain 2 before you want it.
Yeah, we're going to fill up a given orbital. How do I say that?
But you wouldn't, in like 2p, you wouldn't put 1 and then 1 in the next box.
Well, we're going to see that right now, okay? So, and this works in with the analogy, okay? So, we've got 4 electrons in here. We need to put 2 more. So, the fifth one is, he's going to take one of these beds, right? Most likely the one closest to the door, just because he's tired and he just flops down. He's going to sleep right side up. So now let's think about it. The second electron comes into the room. Where's he going to sleep?
In the next one.
He's going to take his own bed, wouldn't you? if there were 3 beds, you take your own, right? So he's going to take the next bed and sleep right side up because he can. These beds, it doesn't matter which one you're sleeping in, you're being charged the same amount. This 4th electron paired up with the 3rd electron in this 2s room in the same bed because they were saving money. They're very motivated by money, by energy. But here, where he has his choice of 3 beds, pairing up with this one or choosing his own bed, he's going to choose his own bed. Does that help? And this is called Hund's rule. And I'm not going to quiz you on the names of those rules. When you're filling orbitals of equal energy, the electrons fill them singly at first, 1 per orbital, and then they double up. Then they double up. Yeah. They're gonna fill singly with parallel spins, meaning they're gonna sleep right side up in the beds. Any questions? This is one of those topics where you're like, I have so many questions, but I don't even know what they are right now, right? You feel like that? Yeah, I'm sorry. The college tells me I have to tell you about this stuff. Okay, so there's a summary of my hotel analogy. So this then is a little bit like a picture of the hotel. It's got this weird upside down shape, not good for earthquake territory because the bottom level is smaller, so that thing's going to fall over in an earthquake. But as you get up, there's more and more rooms, and each of these rooms has more and more beds. These numbers go 1, 2, 3, 4, 5. The number of beds in each of these rooms is odd numbers, 1, 3, 5, 7. Okay, now I told you there's this, Groupon coupons, and there's this mishmash in the ordering. Well, this is one way you can remember the orbital filling. I don't necessarily recommend it, though, but there it is. If that makes sense to you, you go right ahead. But we can also figure this out from the periodic table, which I think is much easier. Question?
For the previous one for carbon, did you show the electron configuration?
No, I didn't. I forgot. Thank you. And I can't resume it because I wrote on something else. Come on. But I can make it again real fast. So we had this, and this, and this. So electron configuration. The 1s has 2 electrons, so 1s with a superscript 2. The 2s has 2 electrons, 2s, 2. And this 2p room has 2 electrons in it, 2p, 2.
But the P can have a maximum of 6, right?
It can have a maximum of 6.
And B can have a maximum of
10.
Okay.
5 beds, 5 orbitals, 2 electrons each, 10. Mm-hmm. So the order of filling is actually hiding on the periodic table. It's amazing. So this one's color-coded. So here, these first 2 columns, those represent S block electrons. How many electrons can fit in an S subshell? 2. There's 2 columns. The P subshell, the P room, has 3 beds. How many electrons can fit in there? 6. How many columns are in the pink section? 6. The pink section represents the P block. The D has 5 beds, 5 different orbitals times 2, 10. Count them. How many columns in the orange there? 10. The F room has 7 beds, 7 orbitals, 14 electrons. Green, 14 columns. It's not a coincidence. What's really amazing is that the periodic table looked like this before the quantum mechanical model was discovered. And yet they fit together so perfectly because they're both describing the same reality. It really is amazing. Except for helium. See, helium and hydrogen, they're the two baby brothers, and they violate all the rules. Like, helium's over here. He's hanging out with the p blocks, but he doesn't have any p electrons. He only has 2 electrons, and they're both in the s sublevel. So, we said that hydrogen had an electron configuration of 1s2. So we've got the periods numbered here. This is 1, this is s, this is the first electron. Helium, in terms of position on the periodic table, would fit over here with this whole orbital filling thing better. If we had helium here, he's 1s2. Once we get past those 2 annoying little guys, then lithium has the first level full, and it has 1 electron in the 2s orbital. Beryllium fills up the 2s, so it has 2s2. When we get to boron, it has 1 more electron, and that electron's going into the 2p room. Carbon has another. That electron also goes into the 2p room. So here's our electron configuration for carbon. It's the previous level being full, 1s2, 2s2, 2p2. Nitrogen, another electron, put that in the 2p. Oxygen, another. Fluorine, another. Neon, another. Neon has that 2p room full up with 6. And the next one would go to the 3rd level, filling up the s room, and then starting to fill up the p room. And this is where the periodic table helps us to remember this staggering. When we come over here, these are s block on the 4th period. So 4s fills before the 3d because it's lower in energy. The 4s room is cheaper than the 3d room, and so the electrons are going to go there. The d room is here. The numbering is a little bit off. How I think of it is, let's look at this. This looks like stair steps, right? And I would expect this one to be up here. Wouldn't that make more sense? You know, I like patterns. So when I look at this, I think that looks like that sank down a level. Like there was a sinkhole or something because the Californians have been using all the water out of the aquifer, and so the whole valley is sinking, kind of a deal. Here's the Central Valley of California sinking. So this isn't the 4D. This is the 3D. So these are this number, 4 minus 1. And so this is this level 5 minus 1. So these are filling up 4D. Let's keep on with where we were. 4s, then we start to fill up the 3D level. And then we get over here. This is regular again. This is 4p. That's going to fill up. We're going to come over here. 5s will fill up. These are sunken. So this isn't 5D, this is 4D. 4D fills up, and then we get to 5P, and those fill up. And then we have 6S, and I don't believe on exams we're going to go any farther than that. Things get even funkier here, but I'll just tell you. So this would be 5D, and then we go into the 4F, because these sank even more. So this is the period number minus 2. The 4F will fill up, and then we'll finish the 5D, 6P, 7S, 6D, 5F, and then back to the 6D. So it's all hiding in there. Here's a summary. Lower energy orbits fill before higher energy ones. Orbitals can hold no more than 2 electrons each, and they have to have opposite spins. When you have orbitals of identical energy, I've got 3 minutes left. When you've got orbitals of identical energy available, they're all going to fill up singly first and then pair up. The electrons are going to take their own bed if they can before they pair up. Okay, so let's look at nitrogen, oxygen, fluorine, and neon. In the essence of time, let's just do oxygen and neon. Oxygen has 8 electrons. So orbital diagram, 1s, 2s, 2p. If I put 8 electrons in here, 1, 2, 3, 4, 5, and the next one is going to go in his own bed. 6, 7. Now he doesn't want to pay for the next room, so he's going to pair up over here. 8 electrons. Electron configuration, 1s2, 2s2, 2p what? 4. If you add those superscripts, 2 plus 2 plus 4 equals 8, that's how many electrons there are. Neon, 10 electrons. 1s, 2s, 2p. Again, 1, 2, 3, 4, 5, 6, 7. Number 8 has to share. 8, 9, 10. Neon has a full set of rooms there. 1s2, 2s2, 2p, 6. That's why it's not reactive. That represents an especially stable configuration in terms of energy. If you get those rooms filled up like that, you get a big discount, okay? And so we're going to see that the bonding and the reactions that elements undergo has to do with trying to get a discount at the Quantum Hotel. See you tomorrow.